Preparation of the hydrocarbon. See, mainly the hydrocarbons are prepared in petroleum from the petroleum and natural gas are the main sources. That is the main sources of alkane. See, we can use some methods, that is unsaturated hydrocarbon, from preparation from the unsaturated hydrocarbon, from alkyl halide, then from the carboxylic acid. First we will see the unsaturated hydrocarbon. Usually the dihydrogen gases are added to alkene. This is the alkene compound, and also alkyne, not only alkene, alkynes also, and the presence of finely divided platinum or palladium or nickel catalyst. So you will get the ethane, that is the hydrogenation process. Because of the presence of hydrogen gas and the catalysis, this process name is called hydrogenation. So you will get ethane. Then similarly propene react with hydrogen gas in the presence of platinum, palladium, nickel, you will get propane. So alkene to alkane. Similar way alkyne, this is propine react with hydrogen gas in the presence of platinum, palladium, nickel catalyst. Using that is you will get propane. Okay, from alkyne to you will get alkanes. See this usually the metals absorbed dihydrogen. Usually the hydrogenation reaction, these metals are absorbed dihydrogen gas on their surface and activate the hydrogen bond. So the platinum and palladium catalyst, this reaction at room temperature, but relatively higher temperature and pressures are required with the nickel catalyst. Next is from alkyl halide. From the alkyl halide, usually they accept fluorides. See, one reaction of zinc and dilute hydrochloric acid gives usually zinc and acid. The presence of acid, you will get that alkane. See, chloromethane react with hydrogen gas in the presence of zinc metal and the dilute hydrochloric acid or any acid, you will get methane and the hydrogen chloride. Similar way, ethyl chloride react with the same manner, you will get ethane and HCl. And the chloropropane, this is also same, only the number of chains only differ. So you will get that similar way, that is propane also will get. Then the alkyl halide, when the alkyl halide are treatment with the sodium metal in the presence of diether gives higher alkane. So this reaction name is called Wood's reaction. See, Wood's reaction is used for the preparation of higher alkanes containing even number of the carbon atoms. So bromomethane react with the sodium metal. So that means two molecules of bromomethane react with sodium metal. The sodium metal bromides are goes away in the presence of dry ether. You will get the pure hydrocarbon. Similar way in ethyl bromide also. Ethyl bromide, 2 moles of ethyl bromide react with sodium metal. You will get N-butane. In the presence of the dry ether, you will get the N-butane. Next method is from carboxylic acid. From the carboxylic acid, preparation of the hydrocarbon. Look at this, the sodium salts of carboxylic acid on heating with the soda lime, that is mixture of sodium hydroxide and the calcium oxide, gives alkane containing one carbon atom less than the carboxylic acid. So usually this process of elimination of the carbon dioxide from the carboxylic acid is called decarboxylation reaction. Now look at this, the sodium acetate react with this water. What happens? It undergoes electrolysis process to form ethane and the carbon dioxide. Here the carbon dioxide gas is evolved. Then this is sodium, or you can tell sodium ethanoate, sodium acetate or sodium ethanoate. Next is the cold reaction. The cold reaction is usually this is the cold reaction. The cold reaction is an aqueous solution of the sodium or potassium salts of the carboxylic acid. This is the carboxylic acid on electrolysis gives alkane containing the even number of carbon atom at the anode. See, this is the reaction. Suppose if you take that the reaction supposed in the following pathway means at anode, at cathode. First at anode is 2CH3 COO minus, lasting of that is 2 electrons are removed, then to form this is the acetate ion, this is the acetate free radical formed, then you will get the methyl free radical and the carbon dioxide. Then the next step, the methyl free radical again react with one methyl free radical, you will get ethane, that is the ethane gas. Then at cathode, H2O and one electron gains, what happens, sorry, one electron lost, so here OH minus and hydrogen free radical is formed, then two hydrogen free radicals are joined, you will get hydrogen gas. Okay, then the properties, physical properties, you will see the alkanes are the almost non-polar molecules because of the covalent nature of the carbon and the carbon hydrogen bonds, and due to very little difference of the electronegativity. Okay, electronegativity between the carbon and the hydrogen atom. Okay. Then they have that is weak van der Waals forces. Due to the weak forces, the first four members, usually C1 to C4, C1 to C4, up to C4 are gases. Then after that, the carbon, fifth carbon to up to 17 carbons are liquid, containing that 18 carbon atoms are more, are that are solid at 298 Kelvin, and they are colorless and odorless mostly. Then the petrol is a mixture of the hydrocarbons and is used as a fuel for the automobiles. Then the petrol and lower fraction of the petroleum also used for the dry cleaning of the clothes to remove the grease stain and things. Okay, so on the basis of the observations, so you can that is many usages are there, that is for hydrocarbon. Next we will see the conformation. Conformation means the conformation, usually the alkanes contain the carbon sigma bond. The electron distribution of the sigma molecular orbital is symmetry, that is the symmetrical around the internuclear axis of the carbon bond. So they have a free rotation, that means they're not disturbed due to the rotation of the axis, so they have free rotation. So the permits free rotations above the say carbon single bond. So the rotation results into different spatial arrangements of atom in space, which can change into the one another. That's mean, see, the spatial arrangements of the atom which can be converted into one another by rotations around the carbon single bonds are called conformations or conformers or rotatomers. Okay, here the alkanes can this have the infinite number of the conformation by rotation around the carbon single bonds. However, it may be remembered that the rotation around the carbon single bond is not completely free. It hindered by a small energy barrier of, that is that 1 to 20 kilojoule per mole. So because of that, they have a weak repulsive interaction between the adjacent bonds. So this type of repulsive interaction is called torsional strain. Simply we called torsional strain. So the conformation of ethane. First we will see the conformations of ethane. This is the ethane molecule. The ethane molecular formula is C2H6. So here the carbon contain the carbon single bond with each carbon atom, and attached 3 hydrogen atom for single carbon atom. So totally 6 hydrogen atoms are attached. So they keep one carbon atom stationary and they rotate the other carbon atom around the carbon axis. So this rotation results to infinite number of the spatial arrangements of hydrogen atoms are attached to the one carbon atom with respect to the hydrogen atom attached to the other carbon atom. So these are all called a conformational isomer. So there are infinite number of the conformations of ethane. However, they are two extreme cases. That is, the conformation of which hydrogen atom attached to two carbon atoms closer together. Look at this. The closer together are called eclipsed form, and the conformations of the other in which the hydrogens are as far apart possible is known as the called staggered conformation. Staggered conformation is called a skew conformation. That is staggered or that skew. See, it may be remembered that in all conformation, the bond angles and the bond lengths remain the same. Eclipsed and the staggered conformation can be represent Sahar's projection and the Newman projection. First, we will see the Sahar's projection. So, in this projection, the molecule is viewed along the molecular axis. It is then projected on the paper by drawing the central carbon-carbon. This is the carbon-carbon bond as a somewhat longer straight chain. This is the longer straight chain. Upper end, this is the upper end of the liner slightly tilted towards right or left hand side. Then the front carbon is shown at the lower end. This is the front carbon. Okay, the front carbon shown at the lower end of the line. So whereas the rear carbon is shown at the upper end. So each carbon has three lines. Look at this. Each carbon has three lines attached to the corresponding to the three hydrogen atoms. So the lines are inclined at the angle of 120 degree to each other. So Sahar's projection of eclipsed form. This is the eclipsed form and the staggered conformation. This is the staggered conformation of the ethane. Okay. Usually the eclipsed form and the staggered form, which is the more stable, mean usually the staggered form conformations are more stable in nature. Then Newman projection. So in this projection, molecules is viewed at the carbon-carbon bond in head-on. So the carbon atom nearer to the eye is represented by a point. Look at this. So three hydrogen atoms are attached to the front carbon. This is the front carbon, and the three lines are drawn here. And the angle is 120 degree to each other. Then the rear carbon. This is the rear carbon. Okay, that this line connected to the rear carbon. So the rear carbon atom is represented by this circle, and the three hydrogen atoms are attached to the shorter line. So this is the rear carbon. So they have each 120 degree angle. So the Newman projection for the ethane is eclipsed form and the staggered form. Here also the staggered conformation is more stable. This angle of this is called angle of rotation or angle of torsion or dihedral angle. So this is the mainly conformations of isomer. Here this is for conformation for ethane. Next, then the relative stability of the conformation. The relative stability of the conformation usually, that is already said, that is the staggered form of ethane. The electron clouds carbon hydrogen bonds are as far apart as possible, so that there are minimum repulsive force, so minimum energy and the maximum stability. Usually minimum energy, maximum stability. So here on the other hand, the staggered form is the changes to the eclipsed form. What happened? The electron clouds of the carbon hydrogen bonds come closer to each other, resulting in increase the electron cloud repulsion. So that check that increase the repulsive force, molecule will have the possess more energy and has less stability. So already I said that is mentioned the repulsive interaction between the electron cloud which affect stability of the conformation. So they are called a torsional strain. Then the magnitude of torsional strain depends upon the angle of rotation about the carbon-carbon single bond. So this angle is also called dihedral. Already said this is dihedral angle or the torsional strain. That is our torsional angle. So of all the conformation of the ethane, the staggered form has the least torsional strain, and the eclipsed form the maximum torsional strain. So thus it may be inferred that rotation around the carbon-carbon single bond is ethane is not completely free. The energy difference between the two extreme form of the order of that is 12.5 kilojoule per mole, which is very small. So even at ordinary temperature, the ethane molecule gain thermal or kinetic energy sufficient enough to overcome this energy barrier, that is 12.5 kilojoule per mole, through the intermolecule collision. So thus it can be said to that the rotation of, about the carbon-carbon single bond in ethane almost free for all practical purposes. So it is not being possible to separate and isolate different conformational isomers of ethane.